So everything is completely clear. Yes?
Yeah, I do understand this inversion transformation.
What aspect of it?
Like the example you gave when you apply I, P, mu, I.
Okay, let's do that. So this is some transformation that does this, right? So let's think geometrically what it does. Let's be in Euclidean space for simplicity. It's clear that it takes the inside of the unit sphere to outside. So in that sense, it's a disconnected conformal transformation. So is it clear what is the conformal transformation? Because if you compute you get this. Just to. And the way to check that is trivial. I mean, you take the derivative. Okay, you want me to take the derivatives, or? Okay. And well, actually do it, and you should find out that, let me think 1 second, it should be 1 over x squared. So it's definitely a conformal transformation. What's peculiar about it is that it's not connected to the identity. It's not a small transformation, it's a large transformation. And furthermore, it's discrete. And then the other thing I wanted to know, that I was a bit fast doing that, but was to show that if I conjugate the translation generator by inversion, that I get the special conformal transformation. Is that what you want to see? So let's do it. So let's act on x mu. Let's first do this transformation. So I have I, P mu acting on x mu over x squared, right? Now let's act P mu on x mu over x squared with some parameter A. Then what do you get? You get, well, x mu over x squared, because now this is a new coordinate from the point of view of this guy, just a shift of this, right? And now I have to invert this new vector. Let's call it y. And from that you get x mu over x squared plus a mu divided by this guy squared. And doing some gymnastics, I mean, trivial gymnastics of multiplying x squared by x squared, you get yes. So this was for a finite transformation. Even now, if I just do an infinitesimal transformation, so that A is small, then we recover precisely the transformation generated by the special conformal generator. So that's what, as an operator, as a set of transformations, conjugating translations by inversion gives you precisely this other transformation. So any other question like that? Yes? Yes. Yeah, so actually someone asked that yesterday. I don't see him. Yeah, so this gives you K. Is this K? Yeah, this is a letter K. This gives you a special conformal. And now you have to just use the fact that you started with these guys. Now by including I in the mixture, I generated for you K, right? And now all that you have to do is look at the commutator of two transformations, one generated by a translation, one generated by a special conformal transformation, and that will give you the dilatations. So you have all the information. These guys already have all the information about the conformal group. Yes. Any other question? Okay. Just in case, I will start by just briefly reminding you the steps we did yesterday before we proceed. So we are on the same page. So in the last lecture, we gave a complete characterization of the set of conformal transformations of flat Minkowski space. And remember that the basic definition of a conformal transformation was a transformation, space-time transformation, that preserved the form of the metric up to scale factor. And in equations, this was just that, some mapping from x to x tilde that preserves the metric. How do I want to write it? Okay, I'm doing it in flat space. Okay. Notice that geometrically, let's develop some intuition about what these conformal transformations do. One of the things that they do is, in Lorentzian signature, it's a Minkowski space. These are transformations that map light rays to light rays. Light rays which are null vectors into each other. Because if I have a null vector, has ds squared equals 0, that's of course preserved by a conformal transformation because it just multiplies 0 by a conformal factor. And in fact, the conformal group, the set of conformal transformations, is the most general mapping of a space-time, of Minkowski space, that maps null vectors to null vectors. So that's one very important property of conformal transformations. And in Euclidean space, it also does something quite fun, which you're going to develop in an exercise, I think it's today, is that it maps. So if you are in RD, so d-dimensional flat space, it maps a conformal transformation maps any n-dimensional sphere to an n-dimensional sphere. So you have a sphere here, and you do some arbitrary conformal transformation. It will map this sphere to some other sphere somewhere else. It will change the size, it will change the location, but it will preserve the mapping. With the caveat, with the clarification that as part of the spheres, we allow degenerate spheres. Where essentially Sn is just Rn, okay? And today in the tutorial, you will find exercises where you'll demonstrate this explicitly, okay? So that's one way of thinking about, that's one way of thinking the geometric action of the conformal group on elementary geometrical objects in space-time. Okay. And then what we saw is by studying the infinitesimal transformations, we analyzed the conformal algebra. We saw that the conformal algebra is that of an orthogonal group. And we saw that the conformal group, the set of conformal transformations which are connected to the identity live in the connected pair of O2, D if we're in Minkowski, in and O1 D plus 1 if we're in Euclidean. Okay? At this point, you might ask, is there a larger set of space-time? But the thing that's very important is that these are a space-time transformation as opposed to many of the symmetries that we have in physics, which are internal transformations, like isospin. So transformations that act on internal degrees of freedom, but not on space-time. So you might very naturally ask, what is if there is a bigger set of space-time transformations other than the conformal transformations, okay? And the answer is both no and yes, but it's yes in a very interesting way. So it's an important theorem which started with, sometimes denoted as Coleman-Mandula theorem. Which actually, even though the people that I think that really did it for the conformal group, something like Lack, Lopuzansky, don't ask me how you spell that, but something, an approximation of this, Lopuzansky and Sonius. The good thing about Google is that even if you misspell, it knows how to find it. Great. The statement is that if you look at, if you take a relativistic quantum field theory, and you want the theory to be non-trivial, which means that the correlation functions are non-trivial, the S matrix is not trivial, the largest possible symmetry group is the direct product of precisely the conformal group times some internal symmetry, which is not a space-time symmetry. So this tells us that really, if you have a non-trivial field theory, the conformal group is the largest space-time symmetry group that you can have. This is not true in 2 dimensions, where you have the whole rich subject of integrability that you probably will hear from Pedro later in the course, in which, in fact, there is an infinite number of other space-time symmetry transformations that have higher spin. The assumption that went into proving this is the assumption that the symmetry transformations are generated by, the infinitesimal symmetry transformations are generated by commutators, so operators that are commuting. The way around this problem is the invention of supersymmetry. So one way of bypassing this is by saying that apart from having symmetry generators that are bosonic, which map bosons to bosons and fermions to fermions, you can postulate a symmetry, which is called supersymmetry, that maps bosons to fermions and fermions to bosons, such that the charges or the generators associated to those transformations are fermionic. And then there is an analogous problem, an analogous theorem that tells you that the largest possible symmetry group of a non-trivial interacting field theory is I'm going to give a ridiculous name because I don't want to specify very carefully how to write this. It will be the superconformal algebra. So there is a notion of the superconformal algebra times possibly some internal symmetry again. Okay. So as far as we know, the most symmetric space-time symmetric quantum field theory could have at most a superconformal algebra. Okay. And if you demand that your quantum field theory propagates particles with helicities of at most 1, then there is the theory that has the largest symmetry is completely fixed. And this is a guy that I already mentioned twice, and you will hear it many, many times by the end of the year, is 4-dimensional, and if you are in 4 dimensions, n equals 4 super Yang-Mills. This is the maximally symmetric field theory that you can have in 4 dimensions. Yes? Now, for example, in 3 dimensions, no, so let me see where.
Like, the maximal is symmetrical and it's also conformal, but it seems something that it is only equal for.
No. For example, if you go in 3 dimensions, there are the maximum symmetric theories will be 3-dimensional superconformal field theories also, but they will not be of Yang-Mills type. So no, but so this is the theorem. The maximal symmetry is always superconformal symmetry.
But you can always find a superconformal symmetry.
Yeah, so it's known, actually, so that's a good question. It's known that you can have a superconformal field theory only in dimensions less or equal than 6. So if you are in, okay, why would you want to go anyway higher? But yes. So you can construct superconformal field theories in any dimension less than 6. Any other question? Yes? The ones that have, for which the edge matrix is not 1. So that if you scatter particles, they just don't go through it. I mean, it's like free field theory is trivial in this respect, that the edge matrix is trivial. Okay. You know, if you wrote the Feynman diagrams, particles just go through each other. Just have free propagation. And therefore, the S matrix, usually we write the S matrix as not doing anything plus some non-trivial transition amplitude that tells you how you have a non-trivial overlap between 2 different sets of initial and final states. And for a trivial theory, for what I mean triviality here, it means theories that have t equals 0. So you just have the identity. There is no dynamics, essentially. Okay. Very good. So we see that conformal and superconformal theories are very special in the space of theories because, in a way, these are the most symmetric theories. And understanding them first, I mean, if there is any hope of solving a 4-dimensional quantum field theory, which is not trivial in that sense, the best hope for doing it is to studying for the most symmetric one, which is exactly this n equals 4. Yes?
If you have a multi-dimensional or you don't get Yang-Mills, you said? What do you get? Is it dependent? Does it depend?
Yes, I mean, that's a complicated story. I can tell you in 3 dimensions. Just very quickly. In 3 dimensions, Yang-Mills is not marginal, but Chern-Simons theories are marginal. So you can have a superconformal Chern-Simons theory in 3 dimensions. And in fact, these theories with maximal supersymmetry in 3 dimensions were only constructed like 1 or 2 years ago. So it's not something that, so there is still lots of interesting things that are being learned. I mean, if you open the archive every few days, there will be an interesting paper addressing these issues. But in particular, the construction of these interesting maximally symmetric theories in 3 dimensions was only done like 1 or 2 years ago. And actually, I was involved in that. Okay. So you probably don't want me to write again what the conformal transformations are. I mean, how they act on coordinates. I think you're professionals right now. Unless someone wants me to do it. Someone wants me? Please say no. Okay, no. Good. Okay, good. And then, okay, so we had this, I guess, just in words, the connected, what we call the usual conformal transformations, which are the connected to the identity. We associated different generators. Okay, I guess I call it mu. Dilatations and special conformal transformations, okay? So these are the generators of the conformal transformations close to the identity. And then we had the inversion, which I already described at some level. I already mentioned most of its important properties, that it's not connected to the identity. The other thing that's also very important is that, well, it's discrete versus continuous. I mean, notice that the transformations in category A are labeled by a continuous parameter. I can make it as large or as big as I want. A discrete transformation is discrete, and it just means that if I do it twice, I come back to myself. Okay. So there is no sense in which you say, I will make a small inversion. It's either there or not there. And the other important property is that it changes the orientation of space-time. So strictly speaking, when we talk about the conformal field theory, what we demand is that the field theory is invariant under transformations A, which are the ones connected to the identity. The conformal field theory may or may not be invariant under inversions, even though in most of our applications it will be invariant under inversions. Yes? Yes? Well, there is a discrete transformation. It is a different matter whether the field theory is symmetric under it or not. But this is a discrete transformation. Yes, but these ones are ones that you know. So notice that the conformal transformations include in particular Poincaré, right? And actually, a very similar statement to this happens there. So in a relativistic quantum field theory, the theory should be invariant under Poincaré transformations that are connected to the identity. And then you have extra discrete transformations that are not connected to the identity, which are parity, time reversal, and PT. And these, again, may or may not be symmetries of the field theory. As I said, the standard model is not invariant under PT. P and T is not invariant. It's invariant under CPT, like that's a theorem, that any quantum field theory is invariant under CPT. So that, of course, therefore here, there are, if you want to be more precise, this group of conformal transformations, OD, D, O2, D, has actually 4 disconnected components. It has the component connected to the identity, which is precisely this one. There is another disconnected component that involves inversion. And then there are 2 other disconnected components that involve parity and PT. So, but in short, the extra discrete transformations that you would have, these are the ones that were anyway in the Poincaré, in the full Poincaré group. Okay. Good. Is there something else I want to say? So, okay, yeah, no. For the time being, let's say there. There's something I could say, but I won't, but I cannot help myself, is that if you, I didn't write them down, but, well, okay, that's the nastiest transformation in any case. The thing to note is that's very different of conformal transformations compared to Poincaré transformations. These are very nonlinear transformations, right? They're very nonlinear functions of the x's. So of course, we all have a good intuition about linear transformations. If you look at something, hopefully you know whether it's Lorentz invariant. But if you look at some other object, it will be hard to know whether it's conformal invariant or not, precisely because the mapping is so nonlinear. So sometimes it is useful, and we may do that later in the course if there is time. There's a useful trick of linearizing, to making linear the conformal transformations. And that's a trick similar to the way how you make manifest the symmetries of a sphere. So imagine you have a 2-dimensional sphere. The 2-dimensional sphere has an SO3 symmetry, right? But this SO3 symmetry is not manifest if I use the spherical coordinates on the sphere, but it becomes totally obvious and manifest if you use some embedding coordinates. So you write S2 as x1 squared plus x2 squared plus x3 squared. Exactly the same can be done for the conformal group. You can go to a space in 2 dimensions higher. So if you're studying your theory in D dimensions, and to be concrete, say Minkowski space, you can embed Minkowski space as a hypersurface in 2 dimensions higher and with signature 2D. And just like in the case of the sphere, the symmetries of the 2 sphere were manifest in the hypersurface embedding, exactly the same thing happens here. You can, this space will have an obvious action of O2, D, and when you restrict it to the hypersurface, it will exactly generate those conformal transformations. Okay? And sometimes it's a useful trick to make quote-unquote manifest conformal transformations. We may do that later when we when we try to fix the dependence of correlation functions of operators in conformal field theories. Yes?
Same as twistor space or some real surface on twistor space?
It's all of this is related to twistor space, but if you want, I can really write down what it is. It is related to twistor space. Yeah. But do people know what twistor space is? I hope you don't.
No, we can talk later.
Okay. If you want, I can tell you later. Essentially, you choose a light cone in this space, a light hypersurface, and then a point in Minkowski space is identified with a light cone in that space, modulo a scale transformation, which is essentially.
Is it the hyperbolic surface in R2, D or 2 plus?
2, well, in D plus 2 dimensions, but with 2 time-like and D space-like components. So it's in 2 dimensions higher. So if I write the hypersurface, you would say this is wrong. If I give you a hypersurface from here to here, the hypersurface will be D plus 1 dimensional, even though the space was D-dimensional. So what's going on? So what you have to do is do a projection. You identify all coordinates up to a scale, and that gives you one extra relation that allows you to go from D plus 2 to D-dimensional. Okay. So now that we are professionals at the symmetries of conformal transformations and what do they do to the various interesting objects like spheres, light rays, and so on. This was just, in some sense, kinematics. Now what we want to explore is the consequences for dynamics of conformal symmetry in field theory. Okay? So now I guess I'll have to remind you, well, hopefully it's a reminder, but if not, let me know, about how we represent continuous symmetries in a quantum field theory and how we extract information from that. So the basic statement about continuous symmetries goes under the name of Nether's theorem. This, by the way, is not restricted to quantum field theory. This goes back to classical mechanics, or essentially whenever you have some symmetry acting on a set of degrees of freedom. The statement of Nether's theorem tells you that if you have a continuous symmetry, like item A in particular, it need not be a space-time symmetry. It can be an internal symmetry. It doesn't matter. Associated to this, the generator of a particular set of continuous transformations, you can associate a conserved current. Or a conservation law. You, of course, are familiar with that from non-relativistic quantum mechanics, that if you have time translational invariance, you have a generator, you have a conserved Hamiltonian, you have translational invariance, you have a conserved momentum, and so on. And then we can define a current, J mu, which is conserved, which just means that the divergence of that current equals 0. Okay? Just like there is a conserved current, there is also a conserved charge. We call it Q, corresponding to that continuous symmetry. And that charge is just the integral, the spatial integral of the 0th component of the current. Okay? Yes? Yes? Yes. 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 So this was what I was saying. So this is just a statement about symmetries of space-time. Now we want to see how these symmetry space-time are realized in field theory, in theories that are invariant under those transformations. So we're now going to construct the operators. So if a given theory has these symmetries, it will necessarily have to have a set of conserved currents. And we're trying to explore what the properties of these conserved currents have to be.
So whenever you say symmetry, in this context, doesn't imply that the Hamiltonian or the Lagrangian is invariant? Or does it imply?
It implies.
From now on?
Yes, because now I'm talking about field theories. So we say that something is a symmetry of a physical system, which is described by some Hamiltonian or Lagrangian, if the symmetry transformation, well, at some fundamental level is a symmetry if it preserves probability amplitudes. But this boils down in the Lagrangian formalism to saying that the Lagrangian is invariant up to a total derivative. So it's a symmetry of the equations of motion. So now let's see that this is conserved. So this equation, of course, you have an intuition about just from undergraduate physics, that this tells you that the time variation of some charge density plus the gradient of some current has to vanish. That's just some conservation law. This, and the fact that this guy is conserved is just estimated if I take the time derivative of this. Now I can replace d0, j0 by the spatial gradient, is it called gradient? Divergence of the spatial current, and then integrating by parts, you get 0, okay? So it's a conserved charge. This charge is also important in the sense that it's precisely, the way you can think about this charge is precisely the operator that generates the transformation, okay? So for example, you know that time translations in quantum mechanics are generated by the Hamiltonian, or translations are generated by the momentum operator. And that's always the case. Whenever you have a conserved charge, this guy is the generator of the corresponding symmetry transformation via Poisson brackets in classical mechanics, via commutators in quantum mechanics. So let me just very briefly, because you've seen this at some level? Okay. So let me just briefly remind you how this arises. Let me do it here. So now let's consider some physical system described by a set of fields phi a of x. This is a collection of fields. I call it phi to call it something, but this could be an arbitrary collection of fields. It could involve a fermion, a gauge field, it doesn't matter. Okay? And the dynamics of this physical system is encoded into a Lagrangian density, but from now on I'm just going to call it a Lagrangian, not keep repeating that, which is a functional of the fields and its derivatives. Okay? Now, something that you know very well is how to derive the equations of motion of the system given a Lagrangian. It's come from the stationary phase by demanding stationarity of this. So let me just review what you get. Of course, you have to get the equations of motion. That's what it means. The equations of motion are the saddle points of this Lagrangian. So you'll get something that's going to be proportional to delta S, that's the action, phi of x. So I'm sorry. So now I want to make some variation. So you know that you have to get something that's proportional to the equations of motion, right? The equations of motion of a system are precisely the variation of the action with respect to the fields. But when you do this derivation, you always remember that you have to do some funny integration by parts. So now let's keep the total derivative term. So when you do this variation, which is you've done many times by now, you get a total derivative, which is this. Is the derivative of the Lagrangian with respect to the derivative of the field times the variation of the field. So right now what I'm doing is just varying the Lagrangian due to doing an infinitesimal variation like this, delta phi of x, okay? Okay, so that's true for any set for any field variation. Okay. It can happen, and it happens usually with the space-time transformations, that the variation of the Lagrangian itself is invariant, is a total derivative. Okay? So can someone give an example of transformation under which the Lagrangian transforms into a total derivative? I essentially said the answer in code. No one? Sorry? Translations, yes. Because under a translation, a scalar field, transform like that, right? Just shift the argument by A. And since the Lagrangian is a scalar under a translation, you get precisely the derivative of the Lagrangian. Okay? Good. No, it can be written this way, I think. It can be written this way, yes.
The equation of motion tells us that the second.
No, the equation of motion is the variation. This is not a derivative, it's a variation. I mean, the equation of motion is the variation of the action with respect to the fields. This is not the equation of motion, right? Yes. No, I think this is completely, maybe it's a bit different than the way you wrote it, but it's completely standard. So now we can define the following object. We can define a Nether's current. So let's define this object, J mu, which is essentially the guy here, the L d mu phi A, delta phi A of x. Now, I write here in general, this will be a total derivative. So I bring it to the other side. So I write it minus k mu of x, okay? And as a consequence of this general variation, what we find is that the divergence of this current is proportional to the equations of motion. Okay? So we constructed an object. So let me review the logic. So we did an arbitrary field transformation like this, okay? That would give you the equations of motion, which is this side. Now we say that this part, now we're going to choose a specific transformation, delta phi A, which is a symmetry. And being a symmetry is the statement that the Lagrangian is invariant up to a total derivative, okay? So I replace, now I'm using the fact that I'm looking at a specific transformation, which is a symmetry, so that the Lagrangian is invariant up to a total derivative, okay? Then we construct an object that under such transformations has this divergence of the current. And now the point is that this current is conserved by using the equations of motion, which is exactly, the equations of motion is just a statement that the variation of the action with respect to the fields vanishes. So therefore, what we've done is construct explicit form of the current that is conserved on shell. Yes.
Minus sign in the equation one before last.
Okay, let's see. Yes. So that's in 3/4 of a blackboard, the statement of Noether's theorem, that given a transformation which is a symmetry, you can construct an associated current that's conserved. Okay? And therefore, you can also associate, of course, by the same, now I can do the thing I said there, you can construct the conserved charge. Can I delete this as an exercise? I mean, that's something you've definitely seen. That's how you derive the equations of motion in the order Lagrange. Sorry? They don't have, sorry? Don't have the same dimension. I'm not sure what you mean.
Oh, so Lagrangian has different dimensions than action.
Yes.
Variation of Lagrangian, which has dimensional.
Okay, I'll.
Minus.
If you want, I can go carefully through the derivation to convince you, but this is, I think, definitely correct. And I don't think.
So, I mean, if you work in units where h bar is equal to 1,
Yes.
an action should be dimensionless, and Lagrangian should be dimensionless. So the variation of the Lagrangian dimension. So the variation of the action with respect to the field and then multiplied by the variation of the field, that should be dimensionless.
Yes.
You have something dimensional on one side and dimensional on the other.
But the point is that the functional derivative of the action with respect to the field does not have the same dimension as the action over the field.
Yes, I think so. I mean, look at this. I mean, under a translation, I think it's better that, I mean, I can go through the derivation in front of you carefully, but maybe it's a good idea that you try to do it in the tutorial. And if tomorrow you still disagree, I promise I do it in the blackboard in front of you. Okay. But you won't, I think. I just don't want to spend time doing this now, or too much time. Okay. Okay, so now this was a general statement about conserved currents, but we're interested in conserved currents associated to conformal transformations. So can someone remind me also, I mean, what is the operator that is associated to translation, the conserved current associated to translations? Well, okay, more generally, is the energy momentum tensor. So, and that makes a lot of sense because if we're making a space-time transformation, which is in particular what a Lorentz transformation, what a Poincaré transformation is, or in this case, in our case, it's going to be a conformal transformation. The current for a space-time transformation is encoded in terms of a very important operator in local quantum field theory, which is the stress energy tensor. D mu, okay? And that makes sense because the stress energy tensor, in some sense, measures the response of the theory to a change in spacetime. That's essentially its definition. So, of course, if you make a spacetime transformation, that will be captured by the stress tensor. Okay. So I already said that the stress tensor first appears when you look at translational invariance. So if I make a transformation x mu going to x mu plus a mu, and you do exactly what I did there, the conserved current associated to translations is written in terms of the stress energy tensor. Okay? It's essentially the product of the stress tensor times the parameter of the transformation. Remember, this is precisely the vector field associated to translations, just a constant. Okay? And now, okay, I have to be a bit pedantic and put a C here. This is the canonical or the Noether stress energy tensor. And if you want, I can write explicitly what it is, just using that general formula. And using the fact that, as I said, that under a translation, the Lagrangian changes like this to a total derivative of the Lagrangian. So just using the general formula, the canonical or Noether stress energy tensor associated to a quantum field theory which has fields phi A is given by this. Okay? Why is this guy here? I mean, can someone tell me? Why is here? Why do I have here the derivative of the field? That's precisely, yeah, because that's precisely how under translations a field changes. Okay. Good. Now, something that's weird about this stress energy tensor, when you first encounter it, is that first of all, it has some couple of annoying properties. One is that it's not necessarily symmetric. Symmetric in mu no. And even more disturbing in some sense, it's not necessarily gauge invariant. So actually, if you compute the canonical stress tensor for electromagnetism, you will find it's not gauge invariant. Like, for example, in electromagnetism. Okay. On the other hand, we know that if we couple, the way we couple our system to gravity, okay, there is a canonical gravitational stress tensor associated to a field theory coupled to gravity that you obtained by, so now on the other hand, there is another notion of a stress tensor, which is the gravitational, which is in fact, this is the way we usually compute the stress tensor. Which you obtain by coupling in an obvious way the theory to gravity. You know how to do that. I mean, you make everything covariant. You replace the Minkowski metric by the covariant, by a curve metric. You replace derivatives by covariant derivatives and so on. And there, the stress tensor is obtained by varying the action with respect to the metric. Okay? So it's absolutely clear that this definition of the gravitational stress tensor doesn't have the pitfalls that this guy and this guy has. It's obviously symmetric, because the metric is a symmetric tensor. And it is obviously gauge invariant, because the Lagrangian is gauge invariant. So if I vary the Lagrangian with respect to the metric, it will preserve the gauge invariant, it will be gauge invariant. So you can say, what's going on here, okay? So I have to do a little detour to tell you what's going on and that everything is fine, don't worry about it. Yes?
No, I was wondering if the difference just was coming from the spin structure of your field.
No, no. So now this is, So there's an infinite number of things that one could say about the stress energy tensor, but life is finite, so just tell you a finite number of things, but that are useful, that will be useful for us. So the first thing to tell you is that the form of the the form of the conserved current is ambiguous. Okay, so there is an ambiguity. So given a conserved current, a conserved current, there exists an ambiguity. Because I can define a new current, J hat mu, which is the original current, plus something which is a total divergence of some, I want to write it like this. Partial nu, V nu, this is a V, this is a nu, mu, okay? With the property that V nu mu is antisymmetric. So if J is a conserved current, then J hat is also a conserved current. Because trivially, if I act on it, use the fact that the original current was conserved, and use the fact that V is antisymmetric, then this guy is also conserved, okay? So from this point of view, not only that, so the new current is conserved, and the other important point is that remember that to any conserved current, we have an associated charge. So if now I construct my new charge, since the difference is the total derivative, you find that the original charge is the same as the improved charge, okay? So there is an inherent ambiguity in the actual definition of a conserved current. And the ability to add these funny-looking terms, these are called the improvement terms. And these are convenient terms that you can add to your conserved currents to make them more desirable. So for example, to make them symmetric, to make them gauge invariant, and so on, okay? Very good. So now the point, so now you should be able to tell me what the resolution of this puzzle was. We had two different looking stress tensor. One was pretty crappy, the other one is wonderful. But the point of the matter is that the two are related by improvement terms. So you can write down the canonical stress tensor, you can improve it to obtain the gravitational stress tensor. Sometimes the improved, better one is called the Delifante stress tensor. This is the guy that figured out, actually, I don't know if it's a guy or a girl, but this person invented, found out that you can always find an improvement term to transform the canonical tensor into the gravitational one. And actually, I've written in my notes here what exactly the form of the transformation is. But since I like you too much, I'm not going to write it down because it's really very messy and not particularly illuminating. But the point is that he found a very explicit expression for this object, which is now antisymmetric in the first two indices. That will transform the canonical to the gravitational tensor. And there is a very explicit form for V that I'm not writing down, but unless someone really wants me to write it down. Anyone wants it? Okay. Was that there was a no, I hope. You want it? Okay. Why did I ask? Let's see. Can I show you later, maybe? If you're the only person? Yes. Okay, so maybe Eduardo will write it in a set of notes. It will take, it's a bit long. But Eduardo will write it in a set of notes and he'll send it to you. Or I can photocopy this page if you can read my handwriting, which is not trivial. Yes?
Is there a way to change the original action so that it's improved?
Yes. That's exactly one way to think about it, yes. So one way to think about the improvement terms, especially when you talk about the stress tensor, is that when you couple a field theory in flat space to gravity, the rules that we have is that you have to you want to write a Lagrangian in curved spacetime that has the property that if you restrict back to flat spacetime, you get the original action. But there are other terms that you could have written down. So let me give you an example. So imagine you want to study, and these are relevant examples. Imagine you're interested in phi to the fourth theory in flat space. Now, if you didn't know any better, you would say, okay, how do I write this in flat space, in curved space, sorry? You write it like this. Okay? But now I have the freedom, without changing anything when I go back to flat space, to add, for example, this term. This guy is called the conformal coupling. Some R phi square term, okay? This is as good as the original action because it has the property that if I go to flat space, you get the same action because the richest scalar of flat space is 0. But the stress tensor that you derive from here and here are different, and they're related by improvement terms. So in the gravitational action, the ambiguity in the choice of improvement terms is in one-to-one correspondence with the possibility of adding new curvature couplings to the Lagrangian when you coupled the theory to gravity. So that's actually how, I think, the most physical way to think about it, that there is a certain ambiguity in coupling the system to gravity, and therefore those that ambiguity is reflected in different stress tensors. But the thing that's important at the end of the day is that the stress tensors measure the same physical quantities. The charge is the same. Okay? But, yes? No, that's what I'm saying. Even that is not unique. Doesn't completely fix the Lagrangian, the stress tensor. But I can always, there is a canonical rotation, a canonical coupling that can make it gauge invariant and symmetric. But then I can still do other improvements.
So we still might not get the gravitational stress tensor?
Well, the gravitational stress tensor, that's what I was, in a way, that's what I'm saying. The gravitational stress tensor is up to you. Are you talking about this coupling or this coupling? And that's exactly the ambiguity. So what's the property of this improved? So there is a lesson for life here, is that you should always try to improve yourself. So what are the properties of, let's now talk about this specific Belifante, which is a particular stress tensor. It has all the nice properties that you would want. So T mu is conserved. It is symmetric, which is totally not obvious. It's totally not obvious, but that's the whole point. And it didn't change the value of the momentum. T canonical, I think I call it T canonical. Yes, well, okay. Yeah. Good. So this was, all this thing was for translations. Now, given this intuition, so I wrote down the stress tensor for translations over there. So can someone guess what the stress tensor, what the conserved current associated to Lorentz transformations will be? Sorry? Sorry? Okay, so what does that mean in formulas? Remember that I gave you the intuition that any space-time transformation, in some sense, is measured by the stress tensor. Precisely, yeah, precisely. You can check it just by doing the calculation, but so do it. So always, and this is the special role that the stress tensor has, it always generates the space-time transformations. All that you have to do is contract the stress tensor with the killing vector. Okay, with the, well, it's killing in this case, okay. Or the vector that generates the transformation, sorry. So infinitesimal vector that generates the corresponding symmetry. Which in the case of Lorentz transformations is omega nu lambda x lambda, right? Is the one that was linear in the coordinates, okay? Sometimes people like to remove the parameter of the transformation from the current, which is a tasteless thing to do, but I'll write it because you may see that in textbooks. Because if you do that, then you get an object that will have 3 indices here. So if I remove this guy from the current, this guy is a constant, right? So I can remove it. Then you can define an object that has 3 indices. So I'm writing this because if you see it in a textbook, but if you see it, you should not read the textbook. It's the physical way to think about it is that you have the stress tensor, and you just couple the stress tensor to the infinitesimal vector field, and the parameter of the transformation is hiding in the infinitesimal vector field. Okay, so this was about vanilla Poincare transformation. So we did translations. Now we did Lorentz transformations. So now the question is, what happens? What about conformal transformations? What about the currents associated to conformal transformations? Okay, so the statement number 1 that I will make, that can be proven, but again, it would be even messier than Mr. Belifante, or Mrs. Belifante, is the statement that if you have a theory that has a conformal symmetry, first of all, by now you should know what the right guess is. You can write this like this. And you can always improve your stress tensor such that the trace of the stress energy tensor is 0, it's traceless, okay? So can always, so if the theory is conformal invariant, then you can find an improved stress tensor that vanishes. Okay? And of course, it can be improved without losing all the properties that we want. Namely, we'll still have the same conserved energy and momentum, the same conserved angular momentum, and so on. Okay? So in a way, this is a very convenient basis in the space of ambiguities of the stress tensor, in which the stress tensor is the expression for the conserved current associated to a space-time transformation level by this vector field is maximally simple. It's just the product of the stress tensor with the corresponding vector field, okay? And now we will see that this precisely does the job. So let's compute the divergence of the current. So I have the divergence of the stress tensor, B nu, plus the stress tensor times the divergence of the vector field V, okay? Now, so this term vanishes. Why? Because in particular, this current includes Poincaré transformations, and from Poincaré transformations alone, we know that the stress tensor is divergence-free. And now from this equation, which I can write, since T mu nu is symmetric in the indices, I can write as A mu B nu plus A nu B mu, right? I haven't done anything. I'm just using the symmetry property of the stress tensor. Now I use the fact that we're looking at conformal transformations. So I use the conformal Killing equation so that the thing in parentheses is 2 over d times eta mu nu times the gradient of B. So we see that for this current to be conserved, we recover the thing that I stated, which is precisely, so this is just proportional times these funny factors and the divergence of B. And this has to vanish, okay? So theories that are conformal invariant, you can associate a stress tensor that's traceless. Do you know of a theory that has a traceless stress tensor that you may have come across? Yes. Precisely. Yeah, that's the simplest example. So is the stress tensor? Have you guys computed the stress tensor for our lambda phi to the 4? Yes? Some people say yes, some people say no. I don't know what that means. So actually, that's a good maybe I'll come back to that later, yeah. So that's an example in which there's an interesting subtlety. I mean, this subtlety I was mentioning here, that there is some freedom in the way you couple the stress tensor to gravity. In the naive way of doing it, you would get a stress tensor whose trace doesn't vanish, but you can improve it away by adding this extra term so that the trace of the stress tensor vanishes. Okay, very good. Should I tell you this more invariant statement or not? Let me just say it very quickly, just for, because, yes. How do you find T mu nu?
Yes, the synthesis doesn't seem to be right.
Oh, this V, okay, this V is just saying that.
Is that a V?
It's a V, yes.
Oh.
Sorry. So this notation was meant to motivate that you have a conserved current associated to each independent infinitesimal vector field. And the stress tensor, if you want, you can just compute it via another and improve it. The claim is that you can always improve it away such that it has this property, that it's traceless, if the theory is conformal invariant. The more invariant statement, so I want to tell you the more invariant statement. So in order to get here, you have to go to very special bases in the set of improvement terms. The more invariant statement is that, oh, I never used this one. Good. The more invariant statement and the reason I'm going through this is because there is a resurgence of interest in this question of scale versus conformal, whether scale symmetry implies conformal symmetry. So I want to make a very precise statement of what is the condition for scale invariance and what is the condition for conformal invariance. And we'll see that to the untrained eye, and even to the trained eye, they look very different. But as far as we know, they're equivalent, at least in all reasonable examples. So if you demand, so I'm not proving this claim, I'm just writing down what the statement is. The first statement is that if you want if the theory is invariant, has a symmetry under special conformal transformations, then the trace of the stress tensor can always be written. If the trace of the stress tensor can be written as the second derivative of any operator, where this is any operator, then the theory is invariant under a special conformal transformations. Okay. Then there is a second statement that if this is true, then you can always cook up a Belifante-like improvement term such that improvement term such that this guy vanishes. And the statement that the theory is invariant under scale transformations or dilatations. So remember, this guy was the K-mu generator. This is the dilatation generator. Then the statement is weaker. The statement is that the trace of the stress tensor is proportional to a gradient of some vector. Okay. So of course, superficially, this condition seems much stronger than this because here you require that this current is further a gradient of something else. Okay. Now you can show, just to repeat what I said already before, that even though this looks like you should be able to find theories that satisfy this property and not this property, there is no reasonable theory that does that. And people are working hard and trying to prove that indeed this implies this. And this has been proven in 2 dimensions. Okay? I mean, the reason I'm mentioning this is because I think it's also more interesting to you if I mention kind of elementary problems that we can talk in half an hour, but that are also kind of at the cutting edge of research. So this is a problem that people are fighting about right now as we speak. Yes?
An equivalence? Is it an equivalent, the special conformal transformation, if and only if d mu mu is d mu d nu x mu nu, or is it going one way? Okay.
Of course, notice that, and that's more or less what I said before. So if I have a special conformal transformations, do I automatically have scale transformations? Someone said yes. Okay, yes, exactly. So 1 implies 2. The question is whether 2 implies 1. Okay, good. So now let me give you a quick example of a very simple case. Let me see how much. As usual, I'm going more slowly than I wanted, but that's life. So let me give you an example where this formal nonsense you can see with your naked eyes. I think you probably have seen this at some level, but maybe you don't. I don't know. So let's consider the stress tensor for 4-dimensional lambda phi to the 4. Then the canonical stress tensor, and that I'm pretty sure you must have computed at some point, is just this. Okay. notice that if I put here T00, you will get precisely the Hamiltonian. Okay, so you can see I'm not telling you big lies or not too many big lies. Essentially, you get 1/2 phi dot square plus the gradient square plus the potential. Okay. Now, of course, this stress tensor is conserved. But now let's compute the trace. Of course, and also you've shown, by the way, I mean, that there was a reason I wanted to do this. Yes, now I remember. The point is that you did an exercise, hopefully yesterday or I don't know when, one of these days, where you were asked to prove that lambda phi to the 4 is conformal invariant. Okay. So now you have to hopefully you check that. And now I want to convince you that this story here is consistent with that statement, but in a subtle way. Because now if I compute the trace of the canonical stress tensor, when you using the equations of motion, you can show that this can be written as d mu of minus phi, d mu phi. So this is really a triviality. Just evaluate this, take the trace, and use the Euler-Lagrange equations. So this, on the one hand, can be written as the gradient divergence of something. So that tells us that it was scale invariant. Good. But also can be written as a second derivative of phi square, which is point number 1. So this implies that it's dilatation invariant, which you knew because you've checked. And this implies the fact that it can be written as a second derivative implies that it's a special conformal invariant. And now, in order to see, now I'll write down what the improvement term would be to go to this wonderful canonical stress tensor, which would be traceless. So now it's easy to see that if I defined T mu nu to be the canonical T mu nu plus I add something here. At first sight, it looks completely ad hoc, but it isn't. So I write this thing. Now, the first observation I want to make is that this guy is still divergence free, so it's conserved. If I act with the derivative here, this guy is precisely cancelled by this guy, so it's a conserved stress tensor. And now I can compute the trace. I'll get the thing that I got before here, T mu mu canonical, plus, if I compute the trace of this term, you get 3a d square phi square. And this guy will vanish if a equals 1/6, okay? So what this tells you is that if you want to find the canonical, or kind of you wish the preferred stress tensor that generates conformal transformations, which is traceless, all that you have to do is add this improvement term. Now you could say, this improvement term, where did it come from? This is some crazy bunch of derivatives. And the point is that it isn't, and let's go back to this statement here. I claim now that if you compute the gravitational stress tensor of this Lagrangian with the inclusion of this Ricci scalar term, and then you set the metric to flat, you get precisely this stress tensor. So this combination is precisely the contribution to the gravitational stress tensor that would arise from coupling phi to curvature. Okay. So there is some logic in this madness. I mean, these terms have a deep geometrical origin in terms of possible terms that you can write down when you couple the field theory to gravity. It's probably, how much, when did I start? So should I continue? Okay. I can go here until tomorrow, but no, that's not true. maybe this is a good place to stop, because the next thing I want to describe is that and we know this already. I mean, here we have shown that lambda phi to the fourth is conformal invariant classically, okay? In particular, well, we've shown that the divergence. So let's focus for the time being now on dilatations. What is the dilatation current? So all that I have to do is, in my master formula for J up there, just put the vector field associated to currents, to dilatations, which is just X. So we have that the dilatation current, which I'm going to call J mu, is T mu nu X nu, right? And what we've seen is that classically, the gradient of d mu, divergence, I keep calling it gradient, the divergence of d mu equals the trace of the stress tensor, which we have shown vanishes if I use this improved stress tensor. And now what I want to discuss next time is something that's important that we already saw in the first two lectures, is that this classical conformal invariance is broken quantum mechanically, because quantum effects make this coupling constant not a constant, but a running coupling that depends on energy. And what we will see is that the first example of something that's very important, deep, and beautiful in field theory is the statement that classical symmetries can be broken by anomalies, broken, and that we usually call, we say that they're anomalous. And we will precisely see in what sense they're anomalous. So in the classical theory, we find that the dilatation current is conserved. And what we will see is that whenever you have an anomaly, what happens quantum mechanically is that the divergence of the current acquires now a non-trivial right-hand side that tells you that it's not conserved. And for the case of dilatations, we will derive what the right-hand side is. And even though the symmetry will be anomalous, it will still be very powerful to have these anomalous conservation laws to put constraints on correlation functions. And then after that, I guess I'll describe in detail what is the operator and Hilbert space description of conformal field theories. You got a question? Oh. Oh, sorry. Oh, this one. This? Oh, sorry.